Hello,
All right, we're
this is
good to go.
Robert Hampton. Oh, okay. Shoot. Can you cut some of this?
Now we can just start from right here. It,
Uh,
yeah,
All right.
just good.
Hello, this is Robert Hampton. With me are Hassan El Turk and Justin Dorning. We are the A team, and our project is the robotic first responder gas detector. The purpose of this robot is to lessen danger for first responders faced by navigating through buildings. And so, what this robot will do is it will search for harmful gases for first responders before they even have to enter the building. Therefore, they can find and isolate the source of a gas leak without entering the building. So, the robot is supposed to detect 3 separate gases and needs to be mobile. So that way it can find whatever gas leak there is. And it's going to need to be able to see to be able to be controlled.
All right. So originally, our three functions were the gas detection, the mobility, and the vision. The first thing that we came across with mobility was the fact that our original plan was to use a robot that was no wider than 3 feet long, with probably a max payload of 100 pounds. We had two motors that could accomplish this goal, but the chassis and track became unfeasible due to COVID-19. The track and chassis we're going to use is around $350, and the only one we could find to get our hands on right now was close to about $1,000, and that was out of our budget. So we changed our track and chassis to a smaller chassis with a max payload of 5 pounds and two 12-volt motors to power those. Now, the second problem that we've run into, or alteration, will be the O2 sensor. We chose the Lumen OX Q20052, which would do 25%, up to 25% of oxygen in the environment. Now, the natural oxygen in an environment right now is 21%. So this would go up to 4% higher. Well, what oxygen does is it allows for things to be more explosive. It's not explosive itself. So we were going to detect when it was higher than normal percentage of oxygen. But the O2 sensor that we used is too sensitive to vibrations for it to be used for our application. And the other O2 sensors that we could find that were in our price range have can only go up to 21%, which would only show us that the oxygen level is at normal percentages, and therefore we decided to forego the O2 sensor and use an MQ5 sensor, which will detect natural gas, and it will be set up very similar to our other sensor, which is the MQ136, which does hydrogen sulfide. And these two sensors are very simple. They have an analog output, which constantly sends data at 100 nanoseconds, every 100 nanoseconds, to our microcontroller, which is the samples of gas. And then from there, we can control how many of those we want to read to our Bluetooth module. The MQ7 we found gave us a little bit of a roadblock. It still works in the same functionality as the other MQ sensors that I just mentioned, but it needs to alter from 5 volts to 1.4 volts and then back to max voltage from the Arduino for longer than 100 nanoseconds, so a sample can be written. And this is done because the 5 volts, the 1.4 volts is turned on for 90 seconds, which allows for different samples to come into the gas sensor. And then the gas sensor then turns on 5 volts to burn any contaminants that may have come into the sensor to make our sampling less accurate. And then the max voltage comes in and it takes the sample right there, which further burns out those contaminants and gives us the most accurate reading that we can possibly give. Now, we decided in the robot camera and to use a robot camera and controller instead of 3D mapping, because the camera and controller, because the 3D mapping wouldn't allow us to get enough data points. It wasn't further developed enough to allow us to get data points to be able to move the robot through that. So we decided to use a camera and controller. And we can go to the next slide. Our requirements and specifications have stayed the same with just slight modifications. The transmitter and receiver is still the same. The camera we have changed to make more cost effective, and I'll go into further that in detail here in a minute. The app is still the same, and the robot, if you can see, the robot is supposed to be less than 3 feet wide, and we still stayed that way. It's just not as big as what we originally planned. Next slide. So concept development, if you look, we have connectivity, power, and size. For our connectivity, the controller has stayed the same with the 2.4 gigahertz radio signal. Sensors are hardwired, and the camera has changed. We're going to use the camera from a phone, which is going to use Bluetooth to connect to our app. So we have changed that in our concept table. The app is now using Bluetooth, and the display is using Bluetooth. We decided to forego the Wi-Fi, and Arduino is hardwired. All the concepts in power and size have stayed the same. So we can go to the next one. Functional decomposition. This is our functional decomp 1. As you can see in our original plan, we were going to use a camera to go to the Arduino, and then from the Arduino to the app. But now we have added a Bluetooth module to connect the Arduino to the app, because at first we were going to use Wi-Fi, but now we're using Bluetooth. The camera now does not connect to the Arduino; it goes straight to the app from a embedded Bluetooth in the camera. Down here at the bottom, you will see that the transmitter goes to the receiver and then to the motor driver and the 2 motors. This concept has stayed the same. We can go to the next slide. As you can see in this slide, we go from the transmitter to receiver, then the motor controller and the motors. The transmitter uses the radio waves, and then from there, it goes to the receiver, which then controls the motor controller, which changes the currents to the motors to function left, right, or straight ahead, full reverse. Then the gas sensors are connected to the microcontroller, which controls the sampling rate. Then the Bluetooth module takes those samples that are fed to it and transmits it over to the app, and then the app displays it. Then in the camera, we have a live video feed, which this is different than our original plan. We're going straight to the app because we're using a phone, smartphone, which has an embedded Bluetooth module in it.
Thank you, Justin. This portion I'll be covering teaming and project management. Our original team roles last semester prior to COVID-19, and as originally planned, that I, Hassan, would be a leader. Justin Dorning would be a spokesperson and recorder. And we had also personal attributes attributed to each one of us, like Robert would be an optimist. Justin would be like a pragmatic challenger to any new idea or change or implementation we wanted to come up with to make sure that our decisions are grounded in reality and could possibly be implemented. And Robert would be an analyst on data, so that's all actually changed this semester. What we currently happen is Justin's a computer engineering student. I'm an electrical engineering, and so is Robert. And Justin was originally going to focus more on the software side because he's stronger at that due to his coursework. But unfortunately, being able to meet up frequently, is I've taken more of a role on the software development side for the app. We'll be utilizing an MIT app developer to be able to connect the Bluetooth from the phone and from the sensors to the Arduino and Bluetooth. Justin has taken on more duties as well. He's also helping out a little bit with the hardware, a little bit of more with the hardware, a little bit with the software with me. And he's still a challenger, and he's essentially a scribe where He takes down a lot of the data that we do, and he's still a challenger in essence. And Robert has taken on different duties as well. He's more on the hardware side now, and he still continues to work as a challenger and an analyst. And he's helped with like our track assembly, for instance. Going on, we originally planned and had our roles designated to each one of us and within a specific time period and where we'd be at. This is our previous project and current activities that we're planning on doing, our time frame within a certain framework of this semester being normal. Originally, we allocated time to our level 1 diagrams, identifying our components, purchasing those components and waiting for their delivery, and testing and integration and robot assembly, including design testing, making sure everything works well. Being able to control the remote controlled robot for gas detection, all that good stuff, including the testing integration, has always, our goals are relatively the same, but just the way we go about them and duties have changed, as shown in this continuing slide. And we also have more data on our hardware that we've purchased, like Justin was speaking. We've taken out certain sensors and implemented new ones due to cost and functionality. Like he was talking about that Luminex oxygen sensor. We'd have to get rid of that because it's not compatible with our design. It's not really good for, it's good for a static environment, but not for a machine that moves around. And it's very sensitive to changes in voltage, current, and being moved around. But here we have, we look at our robot designs for, like, say, level 1 and level 2 decomposition. I believe took more time overall because we had to spend more time coming up with the modules and following the signal more properly. We also combine our work into that, all three of us. We also increased resources for purchasing, increased time for purchasing, testing, and integration, because we had to choose which parts go back and forth and see what works better for our design. So we spent more time on that process. But overall, locating our items took less time than originally. Like our identifying our required components took less time because we had an idea of what we wanted to do. The purchasing time also was relatively the same, but the receiving took a little bit longer. And we also were able to assemble, thanks to that dissemination of like duties, Justin working on, say, the sensors, and Robert assembling the track, and me working on the app. We were actually able to assemble at least the hardware much faster than previously estimated, including like overall combining that together. For the near future, we should be able to finish faster as well. Checking functionality and everything, there's some things we haven't gone to yet, so that's still expected to be exactly the same. But overall, we have done things faster, and this is still a work in progress. So things we've already accomplished have already been changed, including our resources, like I've already covered. We've got more apps and sensors and less hardwired, so we're going to be relying more on Bluetooth connectivity and than we previously were going to do. And that's it. Hopefully